on exam 1.
I only thought there was a front side to this.
If you have your units for Young's modulus in, say, pascals, you know, what was the, I can't remember what the number was, 62.5 gigapascals, like, okay, so you use that to get, and you know, whatever this is, that doesn't have units. You use this to get the compliance matrix. Then when you write your stress, your Voigt stress, that has to be in pascals too. If it's not, everything goes haywire. And so if your Voigt stress is in megapascals, then your Voigt strain is going to be off by 10 to the 6th, by a million. And like, you're close, but that's a pretty significant error if you're going to use that to, you know, for calculations for building something. Okay. Anybody have any other questions about the test right now? I can answer questions about it later too. If you have, I'm not planning to post them, but I have them here. You can look at them. If you have any, you know, if you think I took off more points than I should or fewer points than I should, come talk to me in the next week or whatever. If you just, like, maybe you go home and like you're planning to just let it go and then it just starts to haunt you and you're like, I can't, I got to tell him, you know.
So it's not e to the negative 10?
Nope. For what? No. Okay, so last time we did a problem like this. Where is that? We had a cantilever beam. And there was a torque at the end. And there was a 1,000 Newton force applied. And we calculated tension, shear force, bending moment, and torque as functions of x. But in this case, each of these functions represented the whole beam. But in general, you're going to calculate subfunctions for different parts of the beam, and then your final answers are going to be piecewise functions. So in general, they'll be piecewise functions. So how do you know when you need to calculate a new piecewise function? Or where, you know, where do you need to start using a new subfunction, I guess, for the piecewise function? Where do you need a new subfunction? candidates for those places. There are 4 places where you need to do this. So first, subfunctions, all the functions end at the endpoint. So I guess endpoints, I'll say. Then anywhere that there are point forces. Anywhere that there are point couples. And fourth, where distributed load functions change. We haven't done distributed loads yet, but we will. So locations where the distributed loads or distributed load functions change. Okay. If there are, let's say there are n of these points on the beam, the calculation will require n minus 1 cuts. Yes? For this? This is n with fancy shoes and hat, and n minus 1. Yeah. Okay. That's what the mathematicians call it. Okay, so let's do an example where we have different functions that make up a piecewise function. It's just like just fancy, No, it's just the. No, I'm just drawing I'm just making it like scripty to make a distinction between this and Newton's. Oh. Try harder. Okay, so here's the example. So this time we have a pin joint at the left. A roller in the middle. And a force of 1,000 newtons at the end, where this angle is 30 degrees. And then a torque at the end going this way with a magnitude of 500 Newton meters. What are the internal loads? Well, the first thing we have to do is calculate the external loads at the joints. And again, we're going to neglect the weight on this. We neglected the weight on the last one too. Can you think of why I would be neglecting the weight on this? Well, that would be my justification. There's something that we can't deal with yet, which is why I really ignored it in both of these two cases. And that's that the weight, if you're treating something as a rigid body, it acts at the center of mass. But weight is really a distributed load. And when we start doing cuts, I'd have to deal with the fact that that weight is acting on each one of those cuts in a different way, you know. So anyways, we'll be able to deal with weight once we start talking about distributed loads. Okay, so what kind of load acts at the pin joint? A force vector, good. And then a roller. Oh, one more thing too, actually. So this kind of depends on the specifics of what the joints are like. But this pin joint isn't going to let this thing barrel roll, right? So this is also going to produce torque along the long axis of the beam. We're going to assume that this roller doesn't, although it sort of depends again a little bit on what that joint really looks like. So there's a force RA here and a torque, I'll call it TA here. Then there's an upward force from the roller, call that RB. And then at the end, there's the 500 Newton meter couple. And I guess I might as well break this up into components. So that's going to be 866 and negative 500. So now Newton's second law says RAX, RAY plus 0 RB plus 866 negative 500 is equal to zeros. So this force vector RA is equal to negative 866 for X. Oh, we don't have enough information yet to do B. So RAX is negative 866. And then we have one equation that we'll have to come back to that says RAY plus RB is equal to positive 500. And then the moment equation, I am going to, well, we have to decide which axis we're going to do. I guess I'll do X first. And for the moments about the X-axis, it doesn't matter what I choose as the about point because the only things producing moments about the X-axis are couples. Okay. So we have a positive couple TA and a negative couple 500. So that couple TA is equal to positive 500. And then we'll do the moment equation about the Z-axis. Let's put the about point here. So RA doesn't produce a Z moment about that point. Did I give lengths? Let's pretend I did. Let's see, let's call those each 1 meter. Okay, so the force RA doesn't produce any moment about Z. TA is about X, so that doesn't show up. the force RB produces a moment with a moment arm of 1. So we have 1 times RB. And now we have to think about, so in these, we're just going to take the length horizontally, multiply it by the force, but then we have to think about the direction of the rotation that would cause. So this force RB, make it rotate clockwise or counterclockwise around the about point. Counter, so that's positive. Okay, and now at the other end, does the horizontal force produce a moment? No, the vertical force has a magnitude of 500, a moment arm of 2 meters, and that's a downward force. Would that make it rotate clockwise or counterclockwise? Clockwise, so that one's negative. So we have negative 2 times 500. A 500 Newton meter couple doesn't produce a moment in the z direction. So this is all equal to 0. So we know that RB is 1,000. And now plug that in up here, and you get that RAY is equal to negative 500. This whole length is 2 meters. Yeah. So the moment arm is 2 meters, the force is down. So now our starting point, I'm going to draw a free body diagram of the whole thing. We have this force RA that has values of negative 866, negative 500. We have the couple about the x-axis with a magnitude of positive 500. We have the force RB in the middle of 1,000. And then over here we have the force positive 866, negative 500. And then we have the couple in the negative x direction of 500 Newton meters. Okay. So now we need to look through and find out where the points are that are in that list of places where the subfunctions change. So we want to identify the endpoints, locations of point forces, point couples, and we don't have any distributed loads. Okay, so endpoints, there and there. And now those 2 points are already taken. So anything else that happens at those 2 points, we don't have to count that again. We're only looking for points where we have to deal with these subfunctions changing. So now we're looking for points between those two where we have point forces, point couples, or distributed loads changing. And the only place where that happens is here. There's a point force in the middle. Okay, so n is equal to 3. There's those 3 points where these subfunctions can change. And so that means that we're going to have to do 2 separate cuts. So the first cut is going to represent x values between 0 and 1. So this is for x's in the range of 0 to 1. And for every cut, we're going to start all the way at the left end. And the right end is going to be some arbitrary distance from there. Okay, so this is something that can be sort of confusing. When I give this interval here, I'm not saying that all of the values in our free body diagram are between 0 and 1, non-inclusive. I'm saying the left end of the beam is the left end of our cut, always, and the right end is somewhere in this range. Okay. All right, so there's the cut. And here's the rest of the beam. It's not included in our cut. So here's all the stuff that's happening that isn't showing up in our free body diagram. Somewhere over here, there's the 1,000 Newton force. Somewhere, well, not somewhere, at the end is this 866 negative 500. And then here's that couple. And all of that stuff is happening to the right of what we're isolating. So none of that is going to show up in our free body diagram. What is acting on our isolated piece is this couple of 500 Newton meters. This force vector of negative 866, negative 500. And the only other place that the surroundings make contact with the boundary of what we've isolated are at the attachment between the metal that we've isolated and the metal that we're ignoring. And so those are the internal loads. So that's going to be a tension T, a shear force V, a bending moment M about the z-axis, and a torque, fancy T. Okay, so let's start with Newton's second law. We have negative 866, negative 500, plus the vector t0 plus the vector 0, negative v. I'm just going to write that all as t, negative v. Is equal to zeros. T is equal to positive 866. V is equal to negative 500. And then we'll do the moment equation about the x-axis. .500 Newton meters plus fancy T is equal to 0. So that internal torque is negative 500 Newton meters. And then the moment equation about the z-axis. Always going to use the left end as the about point. So nothing happening at the left end produces a moment. The tension doesn't produce a moment. The torque doesn't produce a moment about the z-axis. So the only things that matter are this m, and that's a couple, so it's just added on, and this v times that moment arm. The length of that moment arm is our arbitrary distance x. So we have m minus vx is equal to 0. It's minus because You have the force of V times this moment arm, and it would make it rotate clockwise. Yes. And I can plug in the value for V. V times X, yes. So M is equal to Vx. Plug in V equals negative 500. And so M is equal to negative 500 X. Okay, so we have these four subfunctions. So these subfunctions work for different values of X. And remember that if you're outside of the range 0 to 1, these don't mean anything, okay? These are only valid for our cut that goes from the left endpoint to an X value between 0 and 1. So now we have to take our second cut. And this cut is valid for all X values between 1 and 2. Okay, so now we're going to see what the internal loads are for different X values in here. But remember that even though our cut is going to be valid for X's between 1 and 2, our isolated piece is still going to start all the way to the left end. Okay, so our isolated piece is going to go all the way from the left end to some X value, and that X value is between 1 and 2. Okay. All right, so here's the piece we're isolating. Here's the piece we're ignoring, and that still has a force vector and a couple. So those are not going to appear in our calculations. We have the force vector of negative 866, negative 500. We have the torque of 500. And now, no matter what X value we choose to define the right endpoint that's in this range, even if we choose the smallest possible piece, that's still like has a right endpoint at like 1.00001, you know? And so we have to include that upward force. So somewhere in here we have the upward force of 1,000. And then we have the internal loads, T, V, M, and torque. Okay? And this distance is X. Okay, so Newton's second law says negative 866, negative 500, plus 0, 1,000, plus T negative V is equal to 0. So T is equal to positive 866. V is equal to positive 500. And now we'll do the moment equation about the x-axis. Positive 500 plus torque is equal to 0. So the internal torque is equal to negative 500 for every x value in between 1 and 2. And then the moment equation about the z-axis, there's no moment produced by these on the left end. There is a moment produced by this 1,000. So what's the moment arm here? That's 1. No matter where x is, that doesn't change where that 1,000 acts. So this could be here, 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 but it's still 1 meter from there to there. So the moment arm is 1. And would that 1,000 Newton force produce a clockwise or counterclockwise moment? Positive counterclockwise. So we have 1 times 1,000, and that's positive. And then the only other things that produce moments about the z-axis are the couple m and negative v times x. So plus m minus vx is equal to 0. So m is equal to Vx minus 1,000. And then substitute in what we know V is, and you get that the bending moment is equal to 500x minus 1,000. Okay, so to get a picture of what's happening, let's plot all of these functions versus x. So here's the tension versus x. There's 1 meter, 2 meters. Here's the shear force versus x. Here's the bending moment versus x. And the torque versus x. I didn't write this before, but the idea is that now these subfunctions represent, these are only valid for x's between 1 and 2. Okay, so let's first look at the tension. For the first cut, from 0 to 1, the tension is positive 866. For the second cut, it's also positive 866. So the tension in this beam is constant with a value of 866. So is the beam in tension or compression? Positive is tension, negative is compression. So yeah, this is in tension the whole way. And now we'll look at the shear force. On the first half, we have a shear force of negative 500. On the second half, we have a shear force of positive 500. What? Okay, so it starts out negative, goes positive. What do we know about what's happening right at this point, x equals 1? nothing, but we're engineers, so we'll pretend we know something about it and draw this. That vertical line doesn't mean anything, but that's how people do it.
Is Y?
What?
Is Y?
Lie?
Yeah, that's why, that's how people do it.
Yeah. Well, really what would happen for real is that point force would be a distributed load spread over a very small amount of space. And yet, so you would have some kind of, it wouldn't be vertical, it would be slanted a little bit. But you'd have something going on that made this a continuous function. So we're just going to write it like this. But probably worth keeping in mind that we don't actually know mathematically, based on our simplification of this problem, we don't know what's happening at x equals 1. Then the bending moment. On the first cut, it's the function negative 500x. On the second cut, it's the function positive 500x minus 1,000. And if you plug that into a graphing thing or thought about it for a while, it would look like this. And that minimum value is right at negative 500. And then the torque, that one never changes the whole way along. It's negative 500 Newton meters on the first half, negative 500 Newton meters on the second half. So that just looks like this. Okay, so if this this beam had the same cross section all the way through and was made out of the same material all the way through, where would you be concerned about this breaking? Like, that's basically the reason why we're doing this analysis. You'd be concerned, so what these three tell you is no matter where you are, the internal loads are about the same. You know, here they switch signs, but that doesn't change anything. This is just as bad for it as this is, and vice versa. The only thing that has, has a preferred location, places where it's less likely to break and more likely to break, is the bending moment. And that says that as you, from either side, approach x equals 1, the bending moment, the internal bending moment is getting bigger, absolute value. So what you would expect is that if this thing was going to break, the fracture would start somewhere close to this. You don't know which side. You can't pick the left versus the right, but you know that things are worse for this beam close to x equals 1 than they are far from x equals 1. Okay.
Can we say it's going to happen more likely on the top half of the beam versus the bottom half where it's in contact?
Okay, so from the internal loads, we cannot say that, but when we calculate the stresses, we will be able to say that. Because remember, the internal loads, we're not making any distinctions about, where is this? So we're not making any distinctions between this point and this point. All we're doing is figuring out what kind of internal loads you have as you move across the beam. But after we're done calculating the internal loads, we're going to use those to calculate stresses that we'll be able to say things are fine here and bad up here, or whatever. So we're not there yet, but that is what we're going to do. Any other questions right now? Okay. That's all. Okay. Okay. So this is principal stresses. Number 2. And so you use the tensile test in number 1 to calculate E and Poisson's ratio. So from number 1, you get E and Poisson's ratio. Do you happen to know what those are? Okay, so we got 181.8 gigapascals, and Poisson's ratio 0.227. Okay, and so now we assume that material that we tested in number 1 has this loading pattern negative 20, 0, 0, 0.4523, 2.5652, 2.5652 there, negative 14.5477. And that's in megapascals. And it asks for the principal stresses and the corresponding principal axes. So if you have a calculator that'll do this for you, you can just calculate this as eigen V L of, put in this matrix. Let's say this in the matrix, and let's call that S actually, stress. Okay, so eigenvalue of this matrix stress, and that'll just spit out these 3 values. Anybody have a 89 titanium? That's the one I'm used to. And now to get a coordinate system that corresponds to that, run eigenvectors with the same matrix. So 20, negative 20, 0, 0, 0.4523, 2.5652, 0, 2.5652, negative 14.5477. Okay, so eigenvector, that's eigen VC of S, gives you a matrix. The axes are the columns of that matrix. So we have 0, 0.164, negative 0.986. Okay. That corresponds to this eigenvalue. The second column is 0, negative 0.986, negative 1.64, nope, 0.164, negative 0.164. And then the third one, the easiest way to do this is just skip the third one for now. Okay, so we'll call this the x-axis. Okay, that's a unit vector. This is a unit vector that's perpendicular to that one. We'll call that the y-axis. And if you have the x and y-axis, how do you get the z-axis? Yeah, just take the cross product of those two. So cross p of this and this gives you the z-axis of your new coordinate system, your principal coordinate system, expressed in your old coordinate system. So it tells you how this new coordinate system is rotated. And then your principal stress tensor in the new coordinate system is just the thing corresponding to your x-axis, negative 15. Your thing corresponding to your y-axis, 0.88. And then your eigenvalue corresponding to your z-axis, negative 20. Any questions about that? Why not just use the third axis that they give you? Okay, so those are not necessarily, so it gives you three eigenvectors that correspond to the three eigenvalues, but it doesn't make sure that they're a right-handed coordinate system. And it could be positive or negative, you know. So if you just assume that these are x and y, and then just find the perpendicular one, what you'll see if you calculate the z-axis this way, and then compare it to the eigenvector, that third eigenvector, you'll see that they're parallel. It's either that same vector or multiplied by a negative 1. I think it asks for the corresponding principal coordinate axis. So most of the time, all we care about are the eigenvalues, but I just want you to keep in mind that those eigenvectors tell you how the new coordinate system is oriented compared to the old coordinate system.